Hello. Uh, we shall consider now some examples with inverse trigonometric functions. I shall do some even problems from the book. First, problems with finding exact value. Find exact value. This is problem 2a. We have one angle. I shall write alpha equals inverse tangent root of 3. We shall call the values of the inverse trigonometric functions angles, and it's good for convenience to use notations alpha, beta, gamma. These are Greek letters usually used for angles. Okay, how to find exact value of this? Now, if I take tangent of alpha, this will be tangent inverse tangent root of 3. Root of 3 is in the domain of the inverse tangent, and by the fundamental identity, this will be root of 3. Tangent inverse tangent of something is something, this something. Okay, now we remember that alpha is between negative pi over 2 and pi over 2. This is the domain of the tangent when we define inverse tangent. This is the range of the inverse tangent. And now we have tangent alpha equals root of 3. We know that alpha is in this interval. What angle could this be? Remembering the table, and this table you have to memorize very well, values of trigonometric functions for some standard angles. So from this table we conclude that alpha should be pi over 3. And that's how we answer our question. That's the exact value of inverse tangent of root of 3. Another example. This will be 4b. Arc sine of 1. Let's say alpha is arc sine of 1. What is this? Exact value. So we have sine alpha will be sine arc sine alpha will be 1, and alpha will be between negative pi over 2, greater or equal, and here less or equal pi over 2, closed interval, the range of the arc sine. And again, we had to answer the question, for what angle in this interval the sine is 1? And there is only one such angle, and this is pi over 2. And that's it. This is our short answer. Exact value. Now, here I want to make a remark. We defined, and we're working with inverse sine, inverse cosine, inverse tangent, and inverse cotangent. Inverse secant and inverse cosecant we are skipping. They are not the popular functions. So when you eventually see a problem like this, just skip it. No inverse secant, inverse cosecant. Okay, we continue. And now I have 6a. We have to find exact value for alpha, which is inverse tangent of tangent 3 pi over 4. What is the exact value here? Well, we have a basic identity. Let's write it down. Inverse tangent x equals x. And this identity is only for x in this domain for the tangent which we have chosen between negative pi over 2 and pi over 2, which is the range of the inverse tangent. Okay, 3 pi over 4 is not in this range. We cannot write that alpha is 3 pi over 4. So how to solve this problem then? I want to write here explicitly alpha is not 3 pi over 4. This angle is not in the range of the inverse tangent. So it isn't this way. Let's look at this angle. Let's make a simple picture. Here, 3 pi over 4, that's the bisector of the second quadrant. It's this angle. Okay, if we continue the second arm of the angle like that, here we come to angle negative pi over 4, measured downward here. Tangent 3 pi over 4 is the same like tangent negative pi over 4. Follows from the definition of tangent. This is a negative value. And now the good thing is that negative pi over 4 gets inside the range of the arctangent, so I can replace it here in alpha. So I can write now alpha is inverse tangent negative pi over 4. And this is exactly negative pi over 4. That's what is alpha. I can use my basic identity because negative pi over 4 is in the right place, in the range of arctangent. So we have to be careful with such evaluations. 6b. Let's do this example. We have to find exact value for cosine arc sine 1/2. How to reason here? Well, this arc sine I shall call alpha again for convenience. And we have that sine alpha is 1/2. And we know that alpha is between negative pi over 2 and pi over 2. Now we can answer what is alpha. So what is alpha? There is only one angle between these two, between negative pi over 2 and pi over 2, where the sine is 1/2. And this is pi over 6. If you're more familiar with 30 degrees, that's a very popular angle. Sine 30 degrees is 1/2. Okay, so alpha is pi over 6. And now we can find cosine alpha. This will be cosine pi over 6. And what is cosine pi over 6? Root of 3 over 2. We solved this problem also. Now, another one which is similar, evaluate cosecant arc cosine 3/5. Okay, arc cosine 3/5, again I'm calling alpha. And it is good to switch immediately to sines and cosines when you have secants and cosecants. These functions are not used, they're not very popular. Sines and cosines are the important function. So here we have 1 over sine alpha. And we have to evaluate this. And what we know is that cosine alpha will be cosine arc cosine 3/5. This will be 3/5. 3/5 is right in the domain of arc cosine. Now what is alpha? Well, it's not one of our standard angles. We don't recognize this value. So we have to reason quite differently. We don't need alpha. Alpha is not needed actually. What we need is sine alpha. And if we know the cosine of one angle, you can find the sine two different ways. First solution, we can use this basic identity, cosine squared alpha plus sine squared alpha will be 1. And since we know what is the cosine, I can write sine squared alpha is 1 minus cosine squared alpha. Here, this will be 1 minus 9 over 25, which will be 16 over 25. And then sine alpha will be 4/5. And then cosecant alpha will be 1 over sine alpha. We had to flip, it will be 5/4. And this is our answer. Second solution. This is very good, very interesting geometric solution. So we model this value on one right triangle, which we can choose any way we want. So let's just draw one right triangle. Okay, and let's think that this alpha here in the lower left corner, this is our alpha. We are given that cosine alpha is 3/5. Cosine alpha, let's write cosine alpha is 3/5. Cosine, this is adjacent to hypotenuse, so we shall put 3 here, and 5 will be the hypotenuse. Now, in this triangle, for this angle, cosine alpha is 3/5. We want to find the sine. So we want to find the other side, and we use Pythagorean theorem. Let's call this side A. 5 squared will be 3 squared plus A squared. A squared will be 25 minus 9 will be 16, so A will be 4. This side is 4. And now sine alpha will be opposite the hypotenuse, will be 4/5. And after finding the sine, we can find its reciprocal, and that's the second solution. So using such a supplementary triangle for geometric solution is very, very helpful. Here is another example. So this is problem 10. That's the number 10. Very interesting. Evaluate cosine inverse tangent of 2 plus inverse tangent of 3. This is inside the cosine. There are two angles inside. Let's call them alpha and beta. So we have alpha is inverse tangent of 2, and beta is inverse tangent of 3. And now we can use a trigonometric formula for a cosine of sum of two angles. Cosine alpha plus beta will be cosine alpha cosine beta minus sine alpha sine beta. Now we have to evaluate cosine alpha cosine beta sine alpha sine beta. Good practice. We shall use again a triangle. We know from the values of alpha and beta that tangent alpha is 2, tangent beta is 3. We shall model this on a triangle for each one separately. Let's first go with alpha. So for alpha we use one right triangle like before. Here I'm drawing a right triangle, and let's say alpha is here angle, this angle down left. We know that tangent alpha is 2. Tangent is opposite to adjacent, so I shall put here 2 and 1. And now I need to find the hypotenuse. If the hypotenuse is a, we have a squared equals 4 plus 1 will be 5. So a will be root of 5. Root of 5. And then we can find all the other angles, all the values of the other trigonometric functions. For instance, cosine alpha will be adjacent to hypotenuse. Let's write here root of 5 is the hypotenuse. So cosine alpha will be 1 over root of 5. Sine alpha will be opposite to hypotenuse, will be 2 over root of 5. We know these two values now. We shall do the same with beta. Again, drawing a triangle, and it doesn't need to be very precise. We can see the beta to be here down on the left corner, left angle, and we model tangent beta is 3, so we put 3 on that side and 1 below. And now what is the hypotenuse? We can tell immediately this will be root of 10. 3 squared plus 1 squared makes 10, and root of 10 is our hypotenuse. So cosine beta is 1 over root of 10. Sine beta is 3 over root of 10. After finding these values, we go back to our problem, and cosine alpha plus beta, this is what we want to find. So I shall write this again, cosine alpha plus beta. That's cosine alpha cosine beta minus sine alpha sine beta. And now we know these values, replacing them here. 1 over root of 5 times 1 over root of 10 minus sine alpha, that's 2 over root of 5, and sine beta 3 over root of 10. Simplifying, common denominator will be root of 5 times root of 10, so this will be root of 50. What we have on the top? 1 minus 6, which is negative 5. It can be simplified even further, because 50 we can write 25 times 2. So root of 50 is root of 25 root of 2. So 5 times root of 2. And then we see that we have negative 1 over root of 2. Cosine alpha plus beta is negative 1 over root of 2. And we can even tell that alpha plus beta will be what? Alpha and beta both are angles in the first quadrant. When you add them, it can be still in the first quadrant or can go to the second quadrant. In the second, obviously, because we have negative cosine, they go to the second quadrant. And what angle the second quadrant has such cosine? This will be 3 pi over 4. Yep. Okay, we solved this problem. Now, let's do some more of the same nature. Find exact value of sine arc sine negative 1/3. Now we can use our basic identity. Because negative 1/3 is in the domain of arc sine, and this I can write immediately is negative 1/3. No hesitation. No need to do anything else. Now, what about cosine arc sine negative 1/3? Okay, now we have to work. We call this angle alpha, like before. We have that sine alpha is negative 1/3. The question is, what is cosine alpha? And again, we can use our triangle, or we can use this identity, cosine squared alpha plus sine squared alpha equals 1. This is, I would say, analytic solution compared to geometric solution. When we know the sine, we can find the cosine. So cosine alpha will be plus minus root 1 minus sine squared alpha plus minus root 1 minus 1/9. So this is plus minus root 8/9. 8/9 we can simplify. Root of 8, this is root of 4 times 2, so this is 2 root of 2. And root of 9, this is 3, of course. Plus or minus, that's important. So sine alpha is negative 1/3. Alpha is between negative pi over 2 and pi over 2. And because the sign is negative, we have angle in the fourth quadrant. Cosine will be positive. So take plus. Cosine alpha will be 2 root of 2 over 3. That's how we reason here. We always have to keep in mind these domains. Okay. Now, let's do another one. What is sine arctangent 10? We follow the same approach. This arctangent we call alpha. So tangent alpha equals 10 sine alpha is what? We can use a triangle, or you can find from the tangent you can find the secant and then tangent, but the best thing will be to use the triangle. Here we draw a triangle, a right triangle, alpha in the same position like before. We model tangent alpha equals 10. Tangent is opposite to adjacent, so 10 here and 1 down next to alpha. And again, have to find the hypotenuse. 10 squared is 100 plus 1, 101. We have root 101. This is the hypotenuse. We know all the sides of this triangle. Now we can find sine alpha. Opposite to hypotenuse, so this will be 10 over 101. This is the sine. We can find cosine if we want. For instance, cosine alpha will be 1 over squared 101. So using this triangle, we can answer many questions. If we have negative values, we can use either the triangle, where we put positive numbers, of course, or we can use the algebraic equation, the basic identity, and work like that. More examples. Simplify this. simplify, this is number 12, y equals tangent arc sine x. X is just a number. We can work here again using our triangle. Arc sine x we call alpha, and we have sine alpha equals x. So we work with this x like we work with any number. In our right triangle, we put alpha here below, and sine is opposite the hypotenuse, so I'm putting x for this side and 1 for the hypotenuse. And the other side, what will it be? If we call it a squared plus x squared equals 1. So a squared is 1 minus x squared. A will be square root 1 minus x squared. This is the set adjacent to alpha. And now, knowing the three sides, I can compute tangent, cosine, whatever. And tangent alpha will be opposite to adjacent, will be x over root 1 minus x squared. So that's our answer. Tangent arc sine x is this. That's right. Tangent arc sine x equals x over root 1 minus x squared. We also found from here, because we have the radio triangle, we have cosine alpha is adjacent to hypotenuse will be root 1 minus x squared. And this tells me that cosine arc sine x equals root 1 minus x squared. Identity true for every x in between -1 and 1. And let's finish with one more. This will be number 14. Evaluate y, which is sine 2 times arc cosine x. What to do here? Well, again, we have to remember trigonometric identities. Sine double angle formula, sine of 2 times something. We have this formula, sine, just a second, it's right on another line. We have to use this, sine 2 times alpha is 2 times sine alpha cosine alpha. So we can write y 2 times sine cosine x cosine sorry, not cosine but arc cosine, sine arc cosine x, and this multiplied by cosine arc cosine x. Well, this second factor will be just x by the basic identity. For the first factor, exactly like above, we find that this is root 1 minus x squared. Sine arc cosine x is this, cosine arc sine x is this. Same work with the same triangle. So we can write y is 2x root 1 minus x squared. And let's stop here for now. Next time we shall talk about derivatives and integrals with inverse trig functions.